In this video, I am going to explain TP questions. The first question is a system with two concentric porous spherical shells of radii Kr and R is shown in figure 11.41. The inner surface of the outer shell is at temperature T1 and the outer surface of the inner shell is at lower temperature Tk. Dry air at Tk is blown outward radially from the inner shell into the intervening space and then through the outer shell develop an expression for the required rate of heat removal from inner sphere as a function of mass rate of flow of the gas. Assume steady laminar flow and low gas velocity. In this example, the equation of continuity and energy are solved to get the temperature distribution. The equation of the motion gives information about the pressure distribution in the system, and this is the figure of this question. Here we have Tk outside and T1 inside temperature, and Kr the inner diameter, and R is the outer diameter of the sphere. And then solution, we postulate that for the system V is delta R Vr is a function of R, and T is temperature is function of R, and density is function of R. The equation of continuity is in spherical coordinates then becomes 1 by R square differential of R square rho Vr equal to 0, and the equation can be integrated to give R square rho Vr is equal to constant, which is Wr upon 4 pi. Here Wr is the radial mass flow rate of the gas. The R component of the equation of motion in spherical coordinate is equation B67, and here we have equation rho Vr differential Vr upon del R equal to minus dp upon dr plus mu uh, bracket differential of 1 by r square d by dr r square Vr, and the viscosity term drops out because integration of this equation then gives uh, pressure is function of R minus pressure is function of capital R equal to Wr upon 32 pi square rho R raised to power 4 and 1 R raised to power 4 by R. Hence the modified pressure uh, pin increases with R, but only very slightly for the low gas velocity assumed here. The energy equation in terms of the temperature in spherical coordinate is according to equation rho Cp Vr dt by dr equal to k1 by r square d by dr of r square dt by dr. Here we have used equation 11.28, for which we assume that the thermal conductivity is constant, the pressure is constant, and there is no viscous dissipation or reasonable assumptions for the problem at hand. When equation 11.422 for the velocity distribution is used for Vr, we obtain the following differential equation for the temperature distribution in the gas between the two shells. dt by dr equal to 4 pi k d by dr r square dt by dr upon wrcp. Here is a graph between transpiration effectiveness and dimensionless transpiration rate 5, and we have the change, we make the change of variable u equal to r square dt by dr and obtain a first order separable differential equation for ur. This may be integrated, and when the boundary condition are applied, we get t minus t1 upon tk minus t1 equal to e raised to power minus r naught upon r minus e raised to power minus r naught by r upon e raised to power minus r naught by kr minus e raised to power minus r naught by r, in which r naught equal to wrcp upon 4 pi k is a constant with units of length. The rate of heat flow towards the inner sphere is q equal to minus 4 pi k square r square qr at r equal to kr, and this is the required rate of heat removal by the refrigerant insertion of Fourier law. The R component of the heat flux gives Q equal to plus 4 pi k square r square k dt by dr r equal to kr. Next we evaluate the temperature gradient at the surface with the uh, aid of equation 11.422 27 to obtain the expression for the heat removal rate Q equal to 4 pi R naught K T1 minus Tk exponential of R naught by Kr 1 minus K whole minus 1 in the limit that the mass flow rate of the gas is 0, so that R naught equal to 0, the heat removal rate becomes Q naught equal to 4 pi Rk T1 minus Tk upon 1 minus K. The fractional reduction in the heat removal as a result of transpiration of the gas is then Q naught minus Q by Q naught equal to 1 minus phi upon e raised to power phi minus 1. Here phi equal to R naught 1 minus K upon Kr equal to WRCP 1 minus Kr K upon 4 pi K Rk is the dimensionless transpiration rate. Equation 11.432 is shown graphically in figure 11.4.2 for small values of phi. The quantity Q naught minus Q upon Q naught approaches the asymptote half phi. This was the first question. Now second question, transpiration cooling. First part, calculate the temperature distribution between the two shells of example 11.44 for radial mass flow rates of 0 and 10 raised to power 5 gram per second for the flowing condition. R equal to capital R equal to 500 microns, TR equal to 300 degrees Celsius, KR equal to 100 microns, TK equal to 100 degrees Celsius, K equal to 6.13 to the power minus 5 calorie per centimeter second degree Celsius, Cp equal to 0.25 calorie per gram second, degree Celsius. B part is compare the rates of heat conduction to the surface at Kr in the presence and absence of convection. Solution of A part. In the absence of transpiration, equation 11.41 is indeterminate, but its limiting form is obtained by expressing the exponential function as a first order Taylor expansion in WR and thus in R naught. T minus T1 upon Tk minus T1 equal to 1 by R minus 1 by R upon 1 by Kr minus 1 by R. This profile designate as theta naught is tabulated here for the present geometry. This is the given table, and now in the presence of transpiration with the given rate WR equal to 1 into 10 to the minus 5 gram per second, and the constant R naught in equation 11.427 is in the presence of transpiration with the given rate WR equal to 1 into 10 to the minus 5 gram per second. The constant R naught in equation 11.427 is R naught 1 into raised to power 5 gram per second into 0.25 calorie per gram second upon 4 pi into 6.13 into the power minus 5 calorie per centimeter second degree Celsius, and it's equal to 0.003245 centimeter, which is 32.45 microns. Now equation 11.427 then gives with then R in microns T minus T1 upon Tk minus T1 equal to exponential of minus 32.45 upon Rx minus exponential of minus 32.45 upon 500 upon exponential of minus 32.45 upon 200 minus exponential of minus 32.45 upon 500. A table of this function here called theta w follows. Here is the table, and now C part is the ratio of the heat conduction to the inner surface R equal to Kr with the uh, lateral transpiration rate to the that with WR equal to 0 is shown in the this equation, and this is the equation, and by putting the values we get 0.876 as the answer. Thus this small rate of transpiration reduces the rate of heat conduction to the inner surface by 12.4%. And now for question number 3, free convection heat loss from a vertical surface. Here is the question. A small heating panel consists essentially of a flat vertical rectangular surface with 30 centimeter high and 50 centimeter wide. We have to estimate the total rate of heat loss from one side of the panel by free convection if the panel surface is at 150 degree Celsius Fahrenheit and surrounding air is at 70 degree Fahrenheit and 1 atm. Use the value C equal to 0.548 of Lorentz in equation, and the value of C are recommended by Whittaker and compare the result of the two calculation. Now solution. The physical properties of the problem are shown follows. Evaluate at an average. Here average temperature we have to calculate T naught plus T1 upon 2, which is 316.5 Kelvin. Beta equal to 1 by T bar, which is 0.00316 Kelvin inverse, and rho bar is PM by R T bar, which is 0.001154 gram per centimeter square cube. And similarly viscosity mu equal to 1.9323 into 10 power minus 4 gram per centimeter second. Now Cp is 1.007 joule per gram Kelvin, which is 0.2407 calorie per gram Kelvin, and K equal to 0.0276 watt per meter Kelvin, and which is 0.6 into 10 power minus calorie per second centimeter Kelvin. The Prandtl and Grashof number are then Prandtl number Cp by mu, and by putting the value of Cp, mu and K we get 0.701, and Grashof number is rho g beta T naught minus T1 into h cube by mu square. After putting the values we get the Gr as 1.34 into 10 power 8. The heat loss rate from one side of the panel, plate, according to equation, is Q equal to WHQ average, which is WC dot K T naught minus T1 G R P R raised to power 1 by 4. With Lorentz value of C, this gives Q equal to, after putting these values, we get Q equal to 7.9 calorie per second, with the value C equal to 0.518 recommended by Whittaker for the air. The result is Q equal to 7.5 calorie per second, and finally we get Q equal to 7.4 calorie per second. Now last question, question number 4. Velocity, temperature and pressure changes in a shock wave. Air at 1 atm and 70 Fahrenheit is following at a upstream match number of 2 across a stationary shock wave. Calculate the following quantities, assuming that gamma is constant at 1.4 and that Cp equal to 0.24 BTU per lbm degree Fahrenheit. And there are three parts, A, B, C, and then A part is the initial velocity of the air. We have to calculate. The B part, the velocity, temperature and pressure downstream from the shock wave, and the last part, C part, the change of internal and kinetic energy across the shock wave. First part, from equation 11.47, the initial air velocity is V1 equal to ma by root gamma r T1 by m, and after putting this value we get 2256 feet per second. And B part, the final velocity V infinity is found from equation this, with zeta tends to infinity, so that phi tends to alpha equal to gamma minus 1 upon gamma plus 1 plus 2 by gamma plus 1 m a1 square. After putting this value we get 0.375, and V infinity we get phi V1 equal to 846 feet per second. The final temperature is obtained from the energy balance, and which is T infinity equal to T1 plus half V1 square V infinity square by Cp, and after putting this value we get 891 R. The final pressure is calculated from the uh, foregoing result by using this equation and the ideal gas law, which is P infinity V infinity by T infinity equal to P1 V1 by T1. Hence hence P infinity equal to P1 V1 by V infinity T1 T infinity by T1, and after putting this value we get 4.4 atm as answer. And C part, the change in specific internal energy is U equal to Cv delta T, which is equal to Cp by gamma delta T, and 0 point, after putting this value we get 62.4 BTU by lbm. And the last, and the change in specific kinetic energy is delta K equal to half, and putting these values we get minus 87.4 BTU per lbm. Thank you for this video.